Hello and welcome to the Vector Software Testing Symposium. My name is Jason Masters and I'm a Senior Field Applications Engineer at Vector, where I've been since 2015. Today I'll be presenting a strategy for static analysis, where we'll look at how to effectively deploy a static analysis solution and how inappropriate static analysis deployment can lead to increased testing times and impact deadlines. We'll also talk about deviations and how they can help optimize the benefits of static analysis. So first of all, we're going to look at why we need static analysis. Then we'll have a look at the wrong way to implement static analysis on a project. And then we'll look at a right way, not necessarily the right way, because there are probably more than one right way to do it, but a right way. We'll then have a look at legacy code and how we handle that. And then we'll have a brief demo of static analysis in action. So why do we have static analysis? Well, software standards that cover software mandate the restriction of the software language to a safer subset. Most of the languages that we might use, like C and C++, have areas in them that are less well defined, harder to use, perhaps depend on the implementation or the platform. And so we want to try and avoid using areas of the language where they are not so well defined. And these restrictions, together with some other code-related constraints, for example, metric thresholds and naming conventions, are collectively called a coding standard. And the only realistic way to enforce a coding standard is with a static analysis tool. Manual analysis is time-consuming, often subjective, not necessarily consistent or repeatable. The thing is most standards don't tell us how to implement static analysis. They say we should use it, but don't give us much guidance on how it should be done. So let's look at a wrong way to do static analysis. A common approach with software development is to dive right in and start writing code. And this is bad for a number of reasons. For example, what about requirements? But static analysis can often be overlooked at the start of development as well. Deciding what tool to use, setting up a tool and configuring it can take time. And there's a belief that some coding standard issues can be addressed quickly and easily later on. And this is due to a lack of understanding of what's in a coding standard and why the rules are there and what they're trying to prevent. It's really a guide and a help to development rather than a set of rules that should be fixed later. There's also a feeling that the flow of coding will be upset by continually addressing coding standard violations, and that the flair and creativity of the developer will be hampered by a coding standard. Quite often a tool might be set up as well, but then the results ignored. So it might be set up as part of the CI process, but then no one bothers to check the reports coming out of the tool. So you can leave static analysis to later on in the project. But when you apply static analysis after all the code's been written, this results or can result in many violations. And you then have to develop a fixing strategy to deal with them. So some issues can be fixed with simple changes to lines of code, for example, adding parentheses to enforce precedence, or adding braces to make statements compound statements. Some might require a little minor refactoring of code to address the order of evaluation issues, for example. Some might require casts or changing the type of a variable, but then what's the impact of that? Some might require changing a function prototype and then checking every call to that function. So some changes can be far-reaching and require multiple changes to many source files. And if we've already got some tests in place for our code, we'll need to rerun those tests to make sure that our fixes of the coding standard violations haven't changed the functionality of our code. And generally, writing code while ignoring the coding standard usually results in many violations. Most of them are easily fixed if discovered when writing the code. Quite often, the amount of work can seem overwhelming if you leave static analysis to later in the project, and this leads to rules being ignored or disabled. And you end up with code that is compliant by deviation. So instead of enforcing all the rules and fixing the code, you accept all the locations where the rules have been broken, and you end up with code, lots of deviations saying why you've broken and where you've broken the rules. But really you're worse than if you did no static analysis at all in that situation. You spent time and effort on that activity, but your code is no better or safer than it was before. You've just spent all your effort into creating deviations for all the violations that exist instead of fixing them or making sure they weren't there in the first place. So in terms of looking at a right way to address static analysis, we need to pick a coding standard and tools. So we can choose a base rule set applicable to our project. So things like MISRA, AutoSAR, and Cert-C coding standards for both C and C++ are very good starting places for coding rules. A lot of them match up very well to the coding standards and the restrictions placed on the programming language. It is possible to write your own rules, your own coding standard, but the off-the-shelf ones have been rigorously reviewed, enhanced, and optimized over a number of years, leading to them to be very good coding standards. You can then choose some additional enforcement as well over and above the rules for the language itself, and these might be driven by company standards or from the customer. So things like metrics, naming convention, code layout, style guideline, things that are perhaps less to do with the code, but more to do with the presentation of the code. You then decide on a static analysis tool, and you can use multiple analysis tools. Some compilers do MISRA checking as well, so you can enable that as well as using an external static analysis tool. You may also need some additional documentation for the coding standard. Some rules require documentation, for example, how floating point numbers are represented in your compiler. And there are other rules that relate to other aspects of the compiler as well that require you to look at the compiler and see if it supports certain features. You may also need a compliance matrix, which documents how you're enforcing the rules, which tool are you using to check which static analysis rule, which coding standard rule. Deviations. Now, deviations are a key part of complying with a coding standard. It's accepted that you can't follow all of the rules all of the time in a coding standard. Inevitably, we're going to meet the real world at some point, either in our embedded software or even on desktop software. We might be running on very fast machines with lots of memory. We still may run into certain constraints where we have to break the rules some of the time. And the coding standards accept this, and we have deviations, a procedure for that. But where we break the rules, we must make sure we do this in a safe and controlled way rather than just breaking them when we feel like it. If we put the deviations in place at the start of the project, it allows developers to not waste time fixing issues that we might not need to address because we're going to deviate from them. So if we know what the deviations are up front, we can make our coding more streamlined. So there's two types of deviation. So we've got sort of project deviations and then specific deviations. So the project-wide deviations are rules that we're not going to obey anywhere in the code. And so we can agree with these beforehand. They may be related to particular compiler features. A compiler may support something or some particular language feature that a coding standard guards against, and we can agree to not follow that rule in that particular case. We may need to document our deviation depending on the type of rule we are breaking. And we may need to have a safety case to justify why we're breaking the rule and why the code we're writing is still safe if we don't follow this particular rule. We can then talk about specific deviations. So this is where we're going to not follow the rules in a particular function or file in the project or on a particular code entity. And these ones are trickier because they may only come up during development when we've implemented some code and it needs to be changed because it doesn't meet some real-world constraint like timing or memory. We may need to recode in a way that breaks some of the rules, but then allows us to get around this constraint. But we may not find out about them until we've written the code. We must document in the same way as for project deviations with a safety case as to why we're breaking the rule. And in some cases, this must be approved by project managers and so on to make sure that we're not just deviating from the rules because we can't be bothered to fix them. We then need to deploy our static analysis tool. We should really integrate this into the development process. The developers are the ones who are writing the code. They're the ones putting the violations in the code. They should be the ones removing the violations from the code. So we need to integrate it into the build system so that we analyze the source files that are in our project. We can also use the correct dependencies, include files and defines that our build process uses when building our files. We should integrate with our compiler so that our static analysis tool can find our compiler header files, knows about all the compiler intrinsic defines and extended keywords. We should integrate with our target so that it knows the data sizes and alignment of our target so that when we do conversions and pointer assignments, we can check for issues there. We should also integrate it with our source code editor so that the coding standard violations appear alongside normal compiler warnings and errors. So this means that we can run the analysis on a source file when we've changed it, and we compile it. So the usual way to do things is to you write some code and then you compile the code and fix any compilation issues. But in this particular case, we can also fix the coding standard violations as well alongside the compiler warnings. We can then also integrate the tool into our CI process so we can run the analysis when we check files in. This catches people who didn't fix the issues when they were compiling the code, but it can also catch link time issues. So if we have a number of developers contributing to the repository, and they may write code that on its own with the code they've checked out is correct, but when it's merged with all the other modifications, some coding standard violations may arise. And these can be sometimes harder to fix because it requires a project level decision on how to fix them. So addressing them when they're checked into the repository is the right time. We can also employ a quality gate and a test before commit so that any code is checked in to the repository. It doesn't make it to the main line of the repository unless it passes all of the coding standards. This point also provides a convenient tap point to upload the coding standard violations to a quality system along with other quality information such as metrics and so on. And this allows other personnel to view the compliance amongst some of the other code quality views. For example, QA people, project managers who don't necessarily have access to the development environment. It gives them a way to view what's going on. Now, very rarely do we start a project with a blank text editor. Most projects aren't greenfield development. There's some code reuse that's perhaps been deployed in the field before from our previous product or been used on a different platform where we're reusing that code on a different target. We've already talked about compliance by deviation, where we analyze the code and then note where all the deviations are, all the violations are, and say, okay, we're happy with that. But we can still use static analysis, but in a slightly modified way. It's still worth running static analysis on the code, but with a smaller subset of rules. So we can ignore any of the advisory rules that are less important, that perhaps relate to things like portability and maintainability, and just use the required and mandatory rules which focus on how the code actually works. We need to look at how many violations there are. Is it possible to address them all? Can the most severe ones be addressed and leave some of the less severe ones? Obviously, this depends on the exact number of violations there are. And then we can baseline the code, accept there are existing violations in the code, and document this. It's also really useful if you can run a functional baseline on the code as well. So you can run the code as it is and run some tests that define how the code works as it is. This is useful because if you then go in and fix some of the coding standard violations, you can run the functional tests again and verify that the fixes haven't broken the way the code works. Of course, we may fix a coding standard violation, which fixes a bug which perhaps the code was relying on to work as it does at the moment. And of course, these things have to be addressed when we find them, but it can happen. Then moving forward, we should apply the full coding standard to any new code. So if we add a new file or a new function to our code, we should use the full coding standard on that new code. When we're modifying existing functions, we should try and use the full coding standard as well and fix all of the issues in that function. This means that we can gradually improve the code as we add new features to the code without sort of going in and fixing all of the issues in one go. So let's have a look at a demo of this in action. So we're going to see how it can be used by a developer on a day-to-day basis. Things like the coding standard, the deviations and tool have already been decided on. So I'm going to be using MISRA C 2012. I've got some project deviations. I'm going to use Visual Studio Code as my IDE. I'm using CMake and Ninja as my build process. My compiler is MinGW GCC. I'm using Git as my version control system, Jenkins as my CI, and I'm using Score to implement my quality gate. So if there are any MISRA violations in the code, the quality gate will fail. So we're going to show static analysis running in the IDE. We're going to look at some violations. We're going to fix them. We're going to add some new code and analyze the new code and see if there's any issues and fix those issues as well. And then every time the code changes, we're going to upload the code to our repository and our continuous integration is going to run through a pipeline, and we'll be able to see the quality gate in action, reflecting the changes we're making as the developer. Okay, so here we have Visual Studio Code. This is my software. It's a Vector Classical Manager Dyna software. So I've got some source code, some header files. I've got a project settings.lnt file which defines my coding standard. So I'm using the MISRA C 2012 coding standard implemented by this LNT file supplied with lint. And then there's two other amendment files which implement the technical amendments to the MISRA coding standard. Now I'm doing something here that you should not be doing in production, and that is turning off warning messages from compiler header files. The MISRA coding standards say that your compiler header file should be MISRA compliant, but for the purposes of this demonstration, I am turning off the messages there because I can't fix them, and so I'm turning them off. But this is something you shouldn't be doing in production. I've got some project deviations, so Directive 4.7 and Rule 17.7. I'm going to ignore the return value of some functions. So it's only these specific functions that I'm ignoring, the fact that I am ignoring the return value from them. If there's any of my own functions in the code and I ignore the return value from them, I will get a violation. Similarly with Rule 21.6, I'm ignoring the fact that I'm using some deprecated functions because I've deemed that they're safe to use. If I use any other deprecated functions, I will get a violation. So we've got some rules that are project-wide deviations, but only for specific code entities. I've also got some project-wide deviations. Directive 4.6, the use of the basic types. Well, I'm ignoring that. I don't really want to use type defs. And there's also another rule I'm ignoring about the implementation of pointer details. So this defines my project-wide deviations, and this is something we can agree on before we start and document to make safety cases as to why we're ignoring these particular messages. A few mechanical things. I've got a build.bat file which builds my software. So I'm using CMake with Ninja, and this can produce a compilation database that contains the information on which files have been compiled and what their dependencies are. And this will be used by lint to work out what files to lint and also what settings to use when we analyze them. So I have a batch file that runs lint. It calls my batch file to build it, and then uses a Python utility that comes with lint to convert the compilation database into a project lint file which lint can understand, which contains the include directories and defines that are used in our build process. I've then got a little bit of code in my batch file here that changes the output format for lint, so that when I run it from Visual Studio Code, I'll use a particular output format that Visual Studio Code can recognize, similar to compilation issues, and so it can put it in the problems window. But when I run from my continuous integration, I want the output in a format that SCORE can understand, which is an XML format. And if I have some of my colleagues who are using different editors, maybe Eclipse or something like that, we can quite easily add a different output format for Eclipse so that the messages will be displayed in a different IDE. And then finally, at the end, we run lint. I'm going to analyze 6 files at a time. There's my project settings, my compiler profile that tells lint how to find my compiler header files and all of my compiler implicit defines, the output selection, and then the project lint, which was derived from the compilation database. And so this means that however I run this file, it will do the build, analyze the files, and produce output in different formats, but using exactly the same settings. Okay, so let's run lint. So I've hit Control-Shift-B. We're building our code. Let's turn on the problems window so we can see what happened. So we can see in the terminal we ran lint, and the problems here are shown here as well. Also, as I change my code, I also upload things to my continuous integration, my pipeline, which is doing the same thing. It's checking out from Git, running lint, uploading to score, and using score as my quality gate. And if we have a look here, we can see we have 4 MISRA violations, and so any MISRA violations will fail the quality gate. And if we come back to here, we see exactly the same 4 violations here reported in Visual Studio Code. So we can double click on them in the same way as compilation messages, and it takes us to the location in code. So we can quite easily fix the issues, find out what they are, fix them. So there's a return in the middle of the function there. We're using some inappropriate arguments to my logical AND. Here I'm using a 0 instead of the null macro. And here I'm mixing the increment operator with some other mathematical operators in an expression. And so I can decide to fix these in a number of ways. I can refactor my code, or I could decide to suppress the message. So here's an example of a specific deviation on a particular line where we're ignoring the lint message on a particular line. So let's fix these errors. So here we're using the null macro. I've decided to fix this error with a specific deviation, and the function here I've refactored so that I don't have the return null. I've just inverted the sense of my if, and then only do things in that particular case. So we've done that. So we've changed our source code so we can rebuild our software. So we can see it's building. We can have a look at how things are going in the terminal. Okay, and there was no messages appeared there, and in fact it reports there that there's no problems have been detected in the workspace. So our code is now completely clear of MISRA issues. We've fixed some by changing the source code, and then we've also addressed one here by putting in a specific deviation. When I changed the code, I also sent it up to my continuous integration pipeline, and so we're now uploading it to score. And then once we've done that, we'll interrogate score and the quality gate to see if we've got any coding standard violations on that particular set of files. We'll come back and have a look at that in a moment. But now we've decided to add some more functionality to our code. So we've got a switch statement here. In our restaurant, we've got a number of dishes here, and perhaps I want to add a new dish to my code so that we've got something else. Okay, so we've finished here, and we can see here that the quality gate is green. And if we have a look here, we can see no MISRA violations, exactly the same as it was in Visual Studio Code, and quality gate has passed. Okay, so if we come back here, let's add a different dish to our menu. I like pasta, so we'll add that. And so we've added a line for pasta. It's also added in some other defines. The Visual Studio is complaining about that now because I haven't done a build, so it hasn't seen the changes in the header file. But we also see that the break is missing here. Now, in this particular case, it might not matter because there's a default afterwards and a break as well. But the trouble is if someone then puts something in the default, then that can change how the pasta route through the switch works. And so we've got a kind of bug lurking, waiting to happen. So the code may work fine. The pasta test cases may pass. And then if someone changes something in default, then suddenly the pasta test cases start going wrong. And some things like that, some issues like that can be really hard to find later on. So we want to try and avoid that. So anyway, so let's run lint on this. Visual Studio Code has seen the updated header, so it's removed those compilation warnings, and now some lint warnings have appeared, telling us that we've departed from the switch syntax, and there's also the flow control where we've got a fall through, and we need to fix that. If we go and have a look at our quality gates, we're still uploading, and we'll see that our quality gate will fail because we've now got our MISRA violations in the same way that the MISRA violations occurred there. So we can come back here and we can let's fix our issues. So we'll add a break in, and then let's run lint again. So Control Shift B to run the build, which runs the normal build process and then runs lint as well. And see if we fixed our issues. Okay, so that's finished, and we have no problems in our workspace. If we switch over to our continuous integration, we can have a look here and have a look at our quality gate, and we can see that it's failed here. So we've got our MISRA violations there in our quality gate, and so that's caught them. And then if we were to wait for this one to finish, we'll see that this one will go green because we have no violations in here. And so this is the kind of typical workflow that we might use when we're developing our code. We write some code, compile our code, build it, and fix the MISRA issues there and then as they occur. The number of issues that appear is usually quite small because we're only adding sort of a bit of code at a time. We get told about them straight away. We can fix them straight away there and then with minimal amount of fuss, minimum amount of impact onto the overall software development. And that is an example of a right way to implement static analysis. And that concludes a strategy for static analysis. We've seen that using static analysis throughout development results in better coding standard compliance, but leaving it until later in the process will cause delays. We've also seen how important deviations are. It's okay to break the rules as long as it's done in a safe and controlled way. Thank you for your attention, and I look forward to answering any questions you have.